we are looking at finishing off related rates. And so there are two questions I want to do. The first one is pretty straightforward, and the last one is horrendous. So you've been warned. So the first one is going to be question 9, or at least one similar to it. And according to Boyle's law, the pressure times the volume of a confined gas is equal to C. And C is a number. C is a constant. So I guess if it's hydrogen, C is one number, but if it's nitrogen, C is a different number, right? But just treat that like 42. On the other hand, P and V are going to change. Pressure and volume are going to change with time, right? So both the pressure and the volume of this thing. So can you imagine they had a cylinder with some gas in it, and they had a piston on the top. Right, so you could compress the gas, right? The piston would come down, the volume would go. You could increase the pressure of the gas, right? So both things change through time. And in this story, you are told the following things. That the snapshot that we're looking at was that the volume was 100 cubic centimeters, that the pressure at this one instant in time was 100 kilopascals, and that the rate at which the pressure was changing at this snapshot in time was 20 kilopascals per minute. So you are told all that, and you are being asked to find the rate at which the volume was changing with time. Okay, so we got a lot to give into us here. First thing is, you don't need to create a connecting formula. There it is, right? Didn't need doing it. So now I'm going to differentiate with respect to T. Now, first thing I'm going to do is differentiate C. What is the derivative of a constant C when you differentiate it with respect to T?
0.
Yeah, big fat 0. Yeah, gone. Don't need to worry about that guy anymore. Now, this is the first time it's actually happened. I want to differentiate P times V with respect to T. How's that going to happen? What am I going to have to do to find the derivative of P times V?
Will you do the product rule?
I am. And I'm going to call that guy P and the guy next to it J. And the product rule, I'll keep to my colour scheme, F dash J plus F of J dash. And that in turn can now become, if you differentiate this guy with respect to T, you get to dP by dt, leave the other guy alone, leave the first guy alone, and differentiate that with respect to T. And it's still equal to 0. And now I can plug and chug. I know this guy is 20. I know the volume of 100. I know the pressure is 100. And I'm trying to find dV by dt equals 0. Yeah, do you see that's coming out really quite neatly, right? There's not an awful lot happening here. That's 2000. So I'll do it up here. So I have 100 dV by dt. That's 2000, which I'm now going to subtract from both sides. And then divide. And the units were cubic centimeters, because it's a volume per minute. Why does it make sense that the rate of change of the volume is a negative number? What is that actually telling us is happening when you increase the pressure of the gas?
It's being compressed and the volume's going down.
And doesn't that make sense from your physics or chemistry? Chemistry, I think, is, doesn't it? Right. I believe there's a fancier version. Isn't there a third one that puts temperature involved as well? What happens when you compress a gas? What happens to the temperature?
It increases.
Yes, it gets warmer. So there's, I can't remember what it is. Is it PVT equals a constant? Is it PV over T? I can't remember. But there's a formula that
PV
has
over nRT.
nRT, there you go. So N and R are just the constant. That's just what C's end up calling it. So it makes sense, and calculus is kind of backing it up. But what we're allowed to do now is attach numbers to situations. So we can actually predict what would happen if you increase the pressure in this system, and the volume would be going down at that rate. So that one was meant to be the relatively straightforward one. This is the last one. And this one is a beauty. First problem, and I wish they hadn't done this, is they don't give you a picture. So I'll just read it out to you, and then I'll create the picture that you need once I get this at me. A Ferris wheel has a radius of 15 meters. It's rotating at a rate of 1 revolution every 2 minutes. Exactly how fast is the rider rising when his seat is 24 meters above the ground level? Now, you read all that information, your first idea is, I don't even know where to start. Where would the Earth how can I get a rate out of that? I don't even really visualize it. So here is the ground. And this is a good reason why pictures are helpful. And we're assuming that the Ferris wheel is a circle that is designed something like that, right? Now, I know that the Ferris wheel is 15 meters. So that vertical distance down is 15. And I'm just going to pick a random point there where the little guy would be, right? There he is. I'm also going to add a line going this way and a line coming down the way. And I'm going to make a little right angle triangle. And that little angle triangle, this distance is a radius, so it's 15. And this distance is going to be h. And this distance, I don't know what it is, so I'm going to call it x. So I've created a right angle triangle that looks something like this. And I'm also going to put an angle theta in here. I'm going to write down here what we've been told. Well, if I return to the question, they've told us that the radius is 15, but I've accounted for that, so I won't worry about that anymore. It does 1 revolution, right? So it goes round, I guess it's going this way, whatever, goes round in 2 minutes. So the rate at which the angle is changing with time. 2 pi in 2 minutes comes out as pi radians per minute. So they have just told me what d theta by dt is. It's pi. They told me that this snapshot distance was 24 meters. So I know that h, this distance, plus that, which is 15, is 24. So they've just told me that the height of h, the distance from here to here, is, whoops, not minutes, is 9 meters. Have you noticed that both the things they told me were not the numbers I end up using, but they allowed me to get the numbers? I now know d theta by dt is pi, and I now know that the value of h is 9 meters. I would also like to know what x is. looking at my picture here, if you know that, I'll draw the guy again. If you know this is 15 and you know this is 9, how will I find x? I know,
Pythagorean.
yeah. Can you trust me it's 12? But you can check it out. So even before we got started in this question, it's like pulling teeth. Wasn't every number that I needed to know, the h number, the x number, and the theta by dt number, every single one of them I had to fight for, right? It wasn't handed to me. I had to figure them out. Now, back to this picture. If you look at this picture, I can create a connecting formula. Sine of theta is opposite over hypotenuse. And that makes h 15 sine theta. Now you might say, well, why did you pick that one? Because there are lots of connecting formula. Couldn't I ignore theta and do a Pythagoras connecting formula? Couldn't have done a connecting formula using theta and x. But the one I chose was theta and h. And that's actually the only decent one to pick, right? The connecting formula that I chose used theta and h. And the reason, don't I know d theta by dt? Oh, and I forgot to put in what we're being asked to find. And we're being asked to find dh by dt. And because I know d theta by dt and I'm being asked to find dh by dt, that's why I went this way. Okay, that's the hardest part over. Setting this thing up was a pain in the butt. Applying it now is going to be easy. Here's my formula. I'm going to differentiate it with respect to t. So dh by dt, differentiate 15 sine theta, you get 15 cosine theta times d theta dt. Now, that wasn't too bad. That's 15. That's whatever this fella is. And that guy there is 2. So there's only one piece of the puzzle missing. And that is, what's the cosine of theta? What number is it? Well, see if I go back to this little triangle, you know, the guy where I have 12. Won't the cosine of theta be 12 adjacent over 15? So the answer we get is 12 pi. That guy there is pi, not 2. I was looking in the wrong place. Right, now that particular question is something you probably want to look at slowly and go over each of the steps and maybe say, okay, what did he do again to get that 12? Why did he choose this formula instead of the others? But it's doable. Not one I would choose to do too many times, but it's doable. And we have finished an entire chapter. We're now on the last chapter. Do you know that analogy, we're on the last lap? Right, that's where we are. So what we're going to do then, we're going to do chapter 4 in particular, chapter 4.1. And we're going to be dealing with max and mins of a function. So we're going to be dealing with the maximum and minimum value of a function. Okay. Well, let's introduce you to some concepts that are going to get used a lot in this section. I can never find things when I want them. Okay. Imagine I have a function that starts here and it goes down, it goes up, and it was a bad choice. There. Starts here finishes here. Let's put in some numbers. This guy is 20. This guy here, -15. This guy here, -8. This guy here, 5, right? So here are some terms that are going to get used. Absolute maximum. The absolute maximum of a function is the largest y value the function can be. So in this question here, would you agree that the absolute maximum is a 20, right? This isn't a function that continues either side. This is a function that starts one place and goes to the other, right? Can you hear me, Jim? Looks like you're trying to fall asleep on me. Right, so maximum value is 20. So I won't write that sentence. I'll just say absolute maximum is 20. And absolute minimum is basically the same sentence with one change. It's the smallest y value the function can be. I'm just not writing the whole words. So in this case, the absolute minimum is -15. So it's terminology. The absolute maximum value of a function is the biggest y coordinate. The absolute minimum is the lowest, right? The smallest y coordinate. And you describe absolute max and absolute min by the values of the y coordinates. So you say the absolute maximum is 10 or the absolute minimum is -50, right? You would say it in that way. Now there's two other guys. There's this guy here, and he is called a local minimum. And in this case, I've got this guy here, and he is called a local maximum. Can you say that a local minimum or a local maximum aren't absolute maximums normally, but they might be in some cases? The way I look at it is a local maximum is like at the top of a hill, and a local minimum is like in the bottom of a valley. Right. So that little part of the world, isn't that a little dip where it gets quite low? And this little part of the world isn't that little hill, right? So if you're looking at a function and you're interested in absolute max and min or local max and min, that's essentially the way I would look at them. And what I'm going to do presently is show you a homework question. Can I do this one more? I can, good. Oops, why isn't that working? Come on, there we go. So this question is question 1. Right. We're going to put down the x coordinate or coordinates, if there's more than one, of where absolute max, min, local max and min work. Right, in this function here, right, it starts at an x coordinate of A, it finishes at S. Where is the absolute maximum going to be? What's its x coordinate?
S.
S. Does this shape have a local maximum as well?
Yes.
Right, and where would that be?
C.
See, would you agree your homework for this question is going to be pretty trivial, right? Does this shape have any local minimums?
Yes.
Give me some letters.
P and R.
Does it have an absolute minimum?
Yeah, also R.
Do you notice that you can be in a local minimum and an absolute minimum at the same time? Right? You can be both, right? So it's not exclusive. If I'm one, I can't be the other, right? I'm Scottish and I am a male, right? I'm allowed to be both at the same time. That's allowed. Here is the next one. There's only 2 examples of this. This shape has some really weird stuff coming on. And what are that weird stuff? Can you see? Oops, I'm not doing that anymore. It's a piecewise function and it's broken up. So I'm going to show you why that causes some problems. This is going to be the nuances, right? The little subtleties that you get in local and absolute max and mins. I'm going to pick a really straightforward function. This function has an absolute maximum of 7. Agreed? Doesn't this function have an absolute minimum of 2? It happens to happen at these 2 places. This function has a local maximum at x equals 5, right? As a local maximum as well. Agreed? Top of a hill, local maximum. That's the highest y value, absolute maximum. No biggies here. Does this shape have a local minimum? No. Can you see any valleys? Nope. So it doesn't have a local minimum. That doesn't seem like too much of a nuance. It is possible for some shapes not to have a local minimum, right? Or even a local maximum. This one is not going to be so pretty. Right at the top of the hill there, the function is undefined. That circle, that hole, means the function is undefined. That shape does not have an absolute maximum. DNE, it does not exist. And you might say, but I can see it's an absolute maximum. It's the top of the hill. You told me it was the top of a hill. It's a top of a hill. It's got one. Nope. You must have that value. Doesn't the function never actually have a value of 7? Well, can't I pick 6.9 then? Well, no, 6.9 isn't the absolute maximum because isn't this function 6.99 somewhere? But I can't use that as my absolute maximum because this function's got a 6.99999. And couldn't I keep doing that till I died? Right, I'd never get a single value that's higher than everybody else. So that function does not have an absolute maximum. It's a DNE.
Did you say that the absolute maximum is in infinitesimal?
No, we don't go there. It's just DNE. Now, let's make life harder. Same function. You know you've seen piecewise functions where they stick dots in funny places? That dot's meant to be a height of 10. Does this function have an absolute maximum? It does, doesn't it? And what's its value?
10.
10. Even although the only part of that function is at that one dot, it still counts as an absolute maximum. Isn't the definition of an absolute maximum nothing to do with shape? It's just, isn't that the biggest y value this function has? And that's all. So you see, it's not always tops of hills, right? Or whatever you want to call it, right? Now, cover that guy up. He's not there. Suppose the dot was here. Because that could happen. Does this function have an absolute maximum? No.
Then
That dot don't help. Because aren't there values bigger than this dot, right? There are places in the function whose y coordinate is bigger. But you can't get to that dot. So it's pretty much the same answer as you would have had if that dot wasn't there. So be on the lookout. Thankfully, it's only for one question, so it's not something that you're going to be spending ages doing. But be on the lookout for holes and breaks and piecewise functions, because those are fraught with danger. That you might think that there's an absolute max or min or a local max and min, and there truly isn't. And I am going to disagree with the book in a minute, but let me show you that as a homework question. Right, oops. Absolute minimum. Tell me the x coordinates, a letter of the alphabet. Absolute minimum.
A or S?
My eyesight's not good with scanning. I think S is a little higher than A. If you agree
lower.
with, right. So A is lower, so it's A. Agreed? Right, so that's good. Absolute maximum.
I think it's R. I can't
I
tell.
agree, it is R. I'm assuming that that's not a vertical asymptote, it's a little corner called a cusp, right? Look at top of your house. Local minimum.
D.
Agreed. Nothing weird happening, right? Bottom of the hill. And this is where we are going to disagree with the book, but I am right and they are wrong. Local maximum.
R.
Agreed. Not disagreeing with the book. Do you know the other one that they gave? And I'm going to disagree with it.
B?
Yes? Is it B? Yeah. They are, oh, I can't put my mouse over it because that writing happens, right? So at B, do you see a dot on the left-hand side of the branch? At B, you see the local maximum? I do not count that as a local maximum. If they want to call that a local maximum, go ahead. Since we're all doing the same question, will you just remember to put a B comma R there so you don't lose points?
Yeah,
But
if that's a local maximum, why would they?
I disagree. I don't think it is, but they think it is.
Why wouldn't they also say C is a local maximum?
Oh, C's got an open circle on it.
I mean, the bit below the open circle.
I don't know is the short answer, but that I wouldn't say that was a local max or min anyway, so I wouldn't be agreeing with them in the first place. So yeah, I don't understand why they would choose one but not the other. I don't like it. Maybe it's just a mistake. Maybe they just accidentally put the wrong answer in. All right, let's pretend it's that. But just so you get the homework points, will you remember to call it B and R? Everything else, we agree. And that's the last time you need to worry about that, because there are no more questions where they do that to you, right? We cool? Right. So in my world, local has to be a little hill or a little valley, right? You're not allowed funny guys like that. Now here's the next question. It just came to me. Can you have two absolute maximums? Well, it depends how I phrase it. Let me phrase it differently. Can you have two places on a curve with an absolute maximum? Yes.
Yes.
Take Take a sine function from 0 to 2 pi. Would you agree that is an absolute max? It's also a local max. Agreed? But if I do a few more cycles, isn't that also another absolute max? Aren't both of them at the same height of 1? So you can have an absolute max happen, right? In this case, at height of 1, and it can happen at a couple of places, right? It's okay, it can happen. So now we're going to look at a concept called critical numbers. Critical number of a function y equals f of x, or the x coordinates, where the derivative is 0 or the derivative is undefined. And there will be quite a lot of questions in 4.1 where you're asked to find critical numbers. So what you're being asked to find are the x coordinates of a curve where the derivative is 0 or the derivative is undefined. And you might think, I wonder why they want us to find critical numbers, why they want these particular values of x. Well, let's show you why that might be a useful thing to do. Can you imagine you've got a nice polynomial, right? One of these guys. What is happening to the value of the derivative at all those local max and mins? What is the derivative equal to at every single one of those local max and mins? 0. So if you want to go hunting for local max and mins, don't you basically want to find the derivative, make it equal to 0 and solve the equation? So all this time that I've been bugging you about style points becomes really important here. Remember, one of the rules of style points is factor the heck out of it. Isn't that going to be helpful when you want to make something equal 0 if it's already factored? Make it look like the original. Make it look pretty. Aren't those also going to help you solve equations? So since you've already had to fight your way through, oh God, he wants us to make it look pretty. Can you see it's actually going to be helpful? Now you might say, well, why is undefined so useful? Well, we've already seen one today. Remember that one that I said that looked like that? By the way, that name to that is called a cusp, if you want to know what it's called. Some functions look like that. Try to remember which one looks like that. God, I had one in the top of my head. I think one of the rational powers looks like that, right? Like a cube root or something would look like that. Anyway, what's the derivative at that corner, at the cusp?
Undefined.
It's undefined. So isn't that also where some, not very many, granted, you won't do this a lot, but aren't there going to be some local max and local mins hiding under an undefined derivative, right? They're going to happen when the derivative is undefined. And so being able to find local max and mins is useful. And the way calculus is going to do it is by finding the critical numbers and then checking them. So let's find some critical numbers. Here's a function. And all we're going to do are find critical numbers. And when you do the homework, there's a whole bunch of questions where that's all they get you to do. Nothing else, just find them, and that's it. So I want to differentiate this function. And I want to do style points. Oops. That's a square. I'll write it again. And I want to do style points. Okay, let's factor the heck out of this guy. What can you do first?
Take out a 3.
Okay. Keep going. Factor
it's-
x squared minus 9.
It's a difference of 2 squares, so it's x plus 3 and x minus 3.
Would you agree that that is going to be pretty easy to solve when it's 0 because we factored the heck out of it? Hasn't style points made our life easier? Right? And what are the two solutions? At x equals -3, the derivative will be 0, and x equals 3, the derivative would be 0. And these are the two critical numbers. And in the homework, you write -3, 3, because they tell you to write it as some, can't remember the wording, but isn't it some blah, blah, comma separated list area. Write the answer down as a comma separated list. That's what it would look like. Now, don't need this for the question, but I can actually do a very primitive sketch of what this thing would look like. Not very neat, but nonetheless. Can you see there's a local max at -3 and a local min at 3? You could plug into Desmos and see that. But isn't this verifying what we already know? That there's a 0 derivative at 3 and there's a 0 derivative at -3. And so I can tell you there's a local max at 3 and a local min at -3. And the reason I can tell you that is I could just go to Desmos and look it up, I guess. But not in this section, but in a later section, we'll show you how to decide local max or min without using Desmos, but only using calculus. Are we good? Let's look for critical numbers of this guy. Well, would you agree there's no style points for this? That's already as good as it's going to get. But we do have an equation to solve. Agreed? Any suggestions for how I could solve this equation?
X equals 0.
Okay. How about I can just tell looking at it that the answer is 0? Because isn't e to the 0 1 and 1 take away 1 gets you 0? I'm assuming that's what Sabrina noticed, right? Nothing wrong with that. It works. I guess if you wanted to do it formally, isn't it that? Now here is a very similar function. Is there a solution to this derivative being 0? Correct, Martin? No. Isn't e to the x always positive something? And if you imagine e to the x, doesn't it? Even in the negative x's, isn't the answer 0.001? It's still positive, and then it climbs up and gets even bigger and positive. So it does not exist. So what's this telling me? It's telling me that this function has a local max or a minimum at 0. Right? We're not quite sure what, but we know one of those two is happening. On the other hand, this function is never equal to 0. Right? If its derivative is never equal to 0, doesn't that mean its derivative is either always positive or always negative? Because you can't go from positive to negative without being 0 somewhere, right? If it's a continuous function, at least. So we are going to, for the last few minutes, a few seconds, whatever, a few minutes. While I'm doing this, you lot say hi, and I'm going to be putting these guys into Desmos so we can have a look at what the thing looks like. And I'm making a prediction that the bottom one does not have a local max and min, and that the top one does. Okay, I think I'm ready. So you're saying hi. Good. Looks like you've all done that. Okay, now the first function that we had was e to the x minus x. So y equals e to the x. I think I can get it down here. Oh, this might just take e. Does this just take e without any problems? Let's find out. Yes, it does. Good. So it's even easier than I thought it was going to be. Let's make that go away. So it's e to the x, take away x. And guess what is happening at x equals 0? Isn't there a local minimum? Actually, it's an absolute minimum as well. And yet, this function oops, like that. Yeah, this function increases forever. You see the blue one? I mean, if I scroll back a bit, can you see it basically just wherever you start, it just keeps on getting bigger. Can you see the difference to a function? One minor change can do. I think I've got time for it. Let's do this guy that I did earlier. The first one, it was x cubed, if I remember right. X cubed, take away 27x. Let's shrink back a little bit. Okay. This has happened to me a few times. Desmos is great, but it's not always perfect. Do you notice that it's very hard to see this function because it has a standardized window? So I'm going to go up here and I'm going to change the x values. And I'm going to do them from -4 to 4. Now I'm going to change the y values, hopefully, to a number that we can use. Right, maybe 60. That looks good. And maybe make this a little bit wider. There we go. That looks pretty good now. There. Can you see that you sometimes have to tweak the windows in X and Y to see what you want to see? Can you see that cubic that I kind of badly drew earlier? That guy. Now, I guess some of you might be thinking, why do I need all this calculus? Can't I just go to Desmos and click on that and click on that? And Desmos will tell you the X coordinates of local max and mins. And you could cheat and do that. But let me tell you why you shouldn't. Well, the first one, cheating is not a good idea because you're not learning anything except how you hit a button on a piece of software and read off a number. That's not good math. Not all x coordinates are going to be 3 and -3. Aren't you going to get x coordinates of √7 or 17/11ths or just weird numbers? If you use Desmos, won't you write down the answer 1.23456 when it's really √17/8 or something? And so I will know that you've cheated and done that. And when I do test questions, I'll be looking for exact values, not decimals. And so you will need to do that. And it's just good math to be able to let the calculus do it. It's nice to use this as a check. In a test, I would definitely do that, right? Go to Desmos and just check it out. That way you know you've got it. But you need to be able to use calculus. Right, that is us. Perfect time.